So in the previous class, we have started discussing about the densification mechanism of the liquid phase sintering process, and we have seen that it occurs in a sequence starting from the formation of the liquid and the penetration of the liquid leading to rearrangement, and then the rearrangement is followed by the dissolution of the solid particles into the liquid, and that is how the liquid then provides a rapid transport path for the solid atoms, which reprecipitate on the surfaces of the larger particles. First, the small particles or the small grains dissolve and then reprecipitate over the larger particles, leading to a process called solution reprecipitation. And in the process, the pores also close, and hence the densification is achieved. Okay. So the liquid penetration is the first step towards this densification, and we had seen that it basically depends on this dihedral angle which forms between the liquid and the solid grains. And when the conditions are such that the dihedral angle is very small, close to 0 degree, then the solid liquid surface energy that you have becomes smaller compared to the solid surface energy, and therefore there is a driving force for the liquid to penetrate this solid interface or the grain boundary in order to reduce the overall energy of the system. Okay, so that's when the liquid penetration happens, and that is defined by this condition. If you take the ratio between gamma SS, which is the solid interfacial energy, to gamma SL, which is the solid liquid interfacial energy, and that becomes more than 2, which you can derive from this. This is the condition where the solid interfacial energy is just balancing the solid liquid interfacial energies. And if you go beyond that, if the dihedral angle falls below this, then the solid surface energy becomes greater than the solid liquid surface energy by a factor of more than 2, or in other words, gamma SS by gamma SL is greater than 2. In that situation, the liquid penetrates the grain boundary. Okay, so this is where the rearrangement process starts, and this is followed by rest of the stages that we are going to discuss in this particular class. Okay, so this sequence of events that you have for the densification process over here can be also illustrated with the help of diagrams like this. So this is the shrinkage which represents the densification, and if you see that as a function of time, you can see the sequence of events leading to the densification. As we discussed, it first starts with the rearrangement. So here in the powder feedstock, you have the parent material, which is the solid, and the additive, which melts when it is heated. So once the liquid melts and it penetrates the solid boundaries, then due to the capillary force exerted by the liquid, the particles rearrange, and as you progress, the pores are filled by the liquid, and the particles ultimately starts to dissolve in the liquid, and the solution precipitation phenomena begins. And beyond that, the solid particles are again reprecipitated, and therefore beyond this stage, you can also expect solid state sintering to take place. Okay, something that you can see over here also. First, the liquid flow, leading to the rearrangement, and then as the particles dissolve in the liquid and then precipitate, that's when this solution and reprecipitation stage starts. And when the reprecipitation is completed, you have all the solid particles back, but with much less porosity between them. right? Then it is in solid phase, because now that all the dissolved particles are reprecipitated, you can also expect a solid phase sintering to occur for the closure of the rest of the pores. Yeah, and these are the events which are again, described with the help of a plot like this, which shows the density as a function of the volume of liquid. Okay, so as we increase the volume of liquid, there are certain changes with regard to the interfaces of the particles, and as you increase the volume, there are different stages of the sintering process which will come into play with different phenomena leading to the densification. Okay, so first, as you heat it, the liquid forms, and there is a solubility for the liquid into the solid and for the solid into the liquid. It is always better to have a small liquid solubility and a higher solid solubility for better densification to happen in this case without any swelling or other issues. And then as the liquid penetrates, rearrangement happens as the volume fraction of the liquid increases. And beyond that, when all the neck regions and the pores are filled by the liquid, then the solid particles start to dissolve. And here we have seen the solubility of the smaller particles are higher compared to the larger particles. So therefore, the smaller particles will dissolve in the liquid and then reprecipitate on the larger ones. Okay, so solution reprecipitation phenomena then starts to happen, leading to not only the dissolution of these particles but also the densification, because this process will also lead to growth of these particles and closure of the pores. And ultimately, when the reprecipitation stage ends, then you have all the solid particles back together with a smaller fraction of pores or with a higher density. Then you can expect the solid state sintering to also take place during the later stage of the process. Okay, so we will take this off one by one to understand in a greater depth. So we will discuss each of these phenomena in detail. We have already discussed about the solubility and the penetration of the liquid as to how it happens and what are the conditions for the liquid to penetrate to the solid boundaries. So now let us talk about the next stage, which is the rearrangement of the particles. Rearrangement occurs when the liquid penetrates into the solid. So here the liquid has to be spread over the compact, so the liquid distribution has to be considered in order to see what is actually happening during this rearrangement process, to understand how this rearrangement occurs as a result of the liquid penetration. So liquid redistribution also kind of happens in a sequence, okay, because here it depends on the volume fraction of the liquid, right? So as you heat it, the liquid forms first, and then with continued heating, the volume fraction of the liquid increases, and as the volume fraction changes, the filling of the solid surfaces or the void spaces between the solid particles will also start to occur, and this fraction of pore filling will also start to change as you increase the volume fraction of the liquid. Okay, so this is what is depicted here in this picture. So when the liquid volume fraction is small, it will be evenly distributed in the neck region that have formed by the liquid and the solid particles at the contact points. Liquid will be distributed mainly along those necks. Okay, now as you increase the volume fraction, this extra liquid that you have after the necks are filled, that will now go to the pores. Okay, and certain fraction of the pores will be filled and the rest of the liquid will remain in the necks. Okay. So that's what you see in this picture in figure B. Here you can see these pores are now filled. A certain fraction of pores are filled, okay, and the rest of the liquid will be now in this neck regions, right? And changing the volume fraction at this stage does not really affect the amount of liquid at the necks, but of course it will alter the fraction of pores that will be filled by the liquid, okay? And once this happens, there is no driving force beyond that. The driving force for this pore filling is the reduction in the surface energy. So once the pores start to fill, the liquid will always tend to redistribute itself due to the reduction in the surface energy. And it doesn't really matter which pores are filled, as long as a certain fraction of pores are filled with the excess liquid that is there after filling the neck, that is enough to redistribute the liquid. And therefore, beyond that point, when a certain fraction of pores are already filled, there is no driving force for the redistribution to take place, okay? And this is what is shown over here in this particular figure C. Here you can see that a certain fraction of pores is filled with the liquid, as you can see, and beyond this point, as I said, there is no driving force for the redistribution to occur, okay? So you can see that the pore filling also happens in a sequence. First, it starts with the neck and then only it goes to the pores, okay? So this picture, this diagram that you have over here, right, this is more like a idealized situation where the powder particles are homogeneously packed and there are only threefold coordinated or triangular pores in between them, and there is no other type of pore or pore size distribution and all that, right? So therefore, this is an ideal scenario. But practically, apart from these threefold coordinated pores, there will be other type of pores also. For example, you can have this kind of six-fold coordinated pores, as you can see from this particular diagram. Apart from threefold pores that you have in these regions, right, you can also have six-fold coordinated pores like these ones, right? So this is a more practical scenario because little bit of inhomogeneity is always expected when the powder is being pressed, and therefore you can expect presence of different types of pores in the green compact, right? So when you have a practical scenario like this, when you have different types of pores having different coordination, then you need to see how the redistribution of the liquid occurs, okay? So let us take this scenario, when you have certain numbers of six-fold coordinated pores also present along with the threefold coordinated pores. So in this case, again, it will happen in a sequence, like how it happened in the case of this idealized situation. At small volume fraction of the liquid, it will only stay in the isolated necks, right? The liquid will be distributed only along the necks when the volume fraction of the liquid is small. And as you increase the volume fraction, first the threefold coordinated pores will be filled by the liquid, like what happened in this case. A certain fraction of the threefold coordinated pores will be filled. The same thing is going to happen in this case also. And now once all the threefold pores are filled, then only the liquid can redistribute itself by filling the necks between the six-fold coordinated pores now, right? So here neck filling happens twice, unlike in this case where the neck filling happened in the beginning itself and after that only the pores were filled, right? But here, since you have two types of pores, one threefold and another six-fold coordinated, you have the necks also distributed around them, around both of these kind of pores, and therefore After the smaller pores are filled, the next, which are around the six-fold coordinated larger pores, will be filled by the liquid. Okay, so that is the third stage. First stage is only filling the isolated necks between the particles. Second stage is filling of the three-fold coordinated pores, and then once this happens, in the third stage, the necks which are there around the six-fold coordinated pores will start to get filled. Okay, and finally in the fourth stage, when these necks around the six-fold coordinated pores are filled, the six-fold pores will be filled. Okay, so here you have 4 stages of pore filling in a sequence like this. Right, so apart from this, even if you have a little more complex situation where you have a distribution of the pore size and presence of different kind of pores, then also this sequential filling of the pores will still be valid. First, the smaller pores will be filled because of their high surface area to volume ratio, and then it will continue in a sequence like this to fill the other kinds of pores. The larger pores will be filled in the later stage of the liquid redistribution process. Okay, but in a scenario like that, when you have a pore size distribution, there are chances that the liquid might find it difficult to reach some of the small pores, and therefore they may remain unfilled. Okay, on the other hand, the larger pores are the last ones to be filled, and therefore in those regions there are chances of inhomogeneities like segregation and things like that, because that is the last liquid to solidify where this kind of phenomena can happen. Right, so therefore the powder compact which is being sintered by the liquid phase sintering process should be a homogeneous one. The powder particles should be packed homogeneously so that there is a narrow pore size distribution which will prevent this kind of inhomogeneous redistribution of the liquid. Now this redistribution can happen in two ways. One is the primary rearrangement, that is basically the rapid rearrangement of the particles soon after the liquid forms. This is basically due to that capillary force which the liquid exerts on the particles once the particle surface is weighted by the liquid. And the secondary rearrangement is basically the invading of the grain boundaries of the solid particles by the liquid phase. Okay, so this is something that we have already discussed, and we have seen that when this surface energy ratio gamma SS by gamma SL, where gamma SS is the solid or the grain boundary surface energy and gamma SL is the solid liquid surface energy, when that ratio is greater than 2, the dihedral angle is very small, and that's when the liquid penetrates the grain boundaries, and as a result of that the particles fragment. Okay, so the secondary rearrangement is about the rearrangement of these fragments which are generated due to the penetration of the liquid phase into the grain boundaries of the solid particles. Okay, so these are the two types of particle rearrangement. One is primary rearrangement and another is secondary rearrangement. The densification by rearrangement depends on the relative amounts of solid and liquid present in the compact during sintering. So let us consider an example in order to understand the effect of the volume fraction of the liquid which is present on the densification by the rearrangement process. So let's say we are talking about a powder compact with a porosity of 40%. So if this compact is sintered by liquid phase sintering, all these pores have to be closed, and if this has to happen by the rearrangement process, it would require a considerable amount of liquid to be present during sintering. That can be shown with a plot like this. Here the volume fraction of the liquid is plotted against volume fraction of shrinkage. So the example that we considered for this powder compact having 40% porosity, it has been shown that a full density can be achieved only by the rearrangement process with 35% liquid. So this half of this plot belongs to the rearrangement process, and the other half is for other processes. So if the liquid fraction is less than 35%, then for full density to occur, other processes have to come into play. And these other processes include mechanisms such as solution reprecipitation. So in principle, it is possible to achieve a full density by rearrangement with a small amount of liquid, but in reality, it is generally observed that rearrangement is difficult when the liquid content is small, if it is say less than 2 to 3 volume percent, particularly when the solid particles have irregular shapes. Okay, right. So that is why practically a considerable amount of liquid is required to achieve full density in liquid phase sintering. Okay, so to summarize this lecture, we can say that the densification in the liquid phase sintering process occurs in a particular sequence of events. It starts with the rearrangement of particles, and that is what we have discussed in this particular class today. When the liquid is formed and the solid particle surface is weighted by the liquid, then the liquid redistribution takes place, which involves a sequential kind of filling. First, the next between the particles will be filled by the liquid, followed by the pores. So as the volume fraction of the liquid is increased, a certain fraction of the pores will be filled, and the driving force behind that is the reduction of the surface energy as the pores are filled by the liquid. Okay, so that means as the solid surface energy is replaced by the solid liquid surface energy, which is lower, it will basically reduce the surface energy, and that's what drives the liquid into the pores. Okay, and once the pores are filled, then we have seen the liquid is redistributed, and once a certain number of pores are filled, there is no driving force for the redistribution beyond that point. And we have also seen that in a practical scenario, there could be different types of pore and different sizes of pore. So we have discussed a scenario where you have 6-fold and 3-fold coordinated pores. So first, the 3-fold coordinated pores will be filled as the liquid redistribution takes place. So in that case, there are basically 4 stages, starting from the filling of the isolated necks, followed by the filling of the 3-fold coordinated pores, which will be followed by filling of the necks, which is around the 6-fold coordinated pores, and finally the 6-fold coordinated pores themselves will be filled by the liquid, right? So when you have different types of pores, this is the sequence of filling that will take place when the liquid is being redistributed. And then finally we talked about the 2 types of particle rearrangement. One is primary rearrangement, which is basically the rearrangement of the particles soon after the liquid forms, and the other one is secondary arrangement, which is induced by the invading of the liquid phase into the grain boundaries of the solid particles. And when that happens, the particles fragment, and the secondary rearrangement process is basically the rearrangement of these fragmented particles. Okay, so with that we come to the end of this lecture. Thank you for your attention.